Mayur, and what a pleasure to be here. And so glad. I mean, there are wonderful, many wonderful photos of Jens. We're glad to find this one. It seems to work well. So yes, Jens, the ultimate PL Renaissance man. So some of my connections with Jens, and only some. I'm sure I'm forgetting a ton. But one was when I was at IBM. Frank, who's here, Frank Tipp, there he is at the back. Was in my department, and he would update me on his work on JAX and the key role that Jens's work and the work the two of them were doing on call graph construction. And that in turn also led me to read Jens's book with Michael Schwarzbach and kind of just get more acquainted and all of that. So that was like, oh yeah, because we had so many static analysis projects going on and we were moving into Java. So marrying it with type analysis was really important. Then I remember a few visits to Purdue when there was this very vibrant community, right, with Jan, Jens, Tony, Suresh. Well, there was a coffee shop where we would just meet there. We wouldn't meet in the department. We'd spend the whole day in that coffee shop. What was it called? I forget, but anyway, yeah. I found this community for me at IBM when we were kicking off projects like the Extend language that I'll talk about, the JIX RVM, later when we were doing Eclipse and the Eclipse Innovation Grants. This group, Gang of Four was always a great sounding board, always very enthusiastic, and also giving us good feedback about how things would be received by academics and so on. And one example of that was the encouragement, especially that Jens had for us with the Extend language project. And in fact, his student, Christian, who's here, was an intern at IBM and was a primary contributor to the original, there he is, the Extend project. And then I will say a little bit about the paper that Jonathan Lee and Jens had on featherweight Extend. And then there was this concurrent collections programming model led by Kat Nobe, and it played a key role in our NSF Expedition Center, which when I was at Rice, we were working with UCLA, and Jens played a key role there that I'll talk about. And then we had so many other interests, like register allocation. There was work that Jens was doing with his student Krishna, who's over here, and Fernando Pereira, and so on. So it's really great to have all these connections. So what I thought I'd do for the talk is just do a deep dive on one of them. Well, why is this going? About the featherweight Extend paper. So Jens may not be aware, and many of you may not be aware, even though my background is more high-performance computing and compilers, the grad students twisted my arm at Georgia Tech to create, Chirun is aware because he's my colleague at Georgia Tech, create this class, CS6390, which is programming languages, where we got a lot of material from Bob Harper, Benjamin Pierce. It was, STLC, all that good stuff. And towards the end, I actually do a lecture on featherweight Extend. So, in fact, many of the class projects, because people could choose what they want, ended up being extensions of featherweight Extend. So the background was we at IBM, this is with my good friend Vijay Saraswat and others, had created this language called Extend that was presented in UPSLA 2005 in the Onward track, I remember. And it was really focused on how to make distributed parallel high-performance computing more productive. And there was this notion of places, which is now getting increasingly important with heterogeneous computing and so on. And this locality rule that all data accesses have to be local. And so that was the paper. And there were two of the key constructs that we are still using in my group's research is this idea of async and finish. They nest very nicely in a grammar that Jens then formalized in the featherweight Extend paper. So async around any statement indicates that that's an asynchronous execution of that statement. The implementation is free to execute statement 1 before or in parallel with statement 2 or after statement 2, it's asynchronous. And then there's this finish construct, which is also lexically scoped, unlike a barrier or a wait operation, where everything in the scope of finish, you can only proceed beyond the scope of finish after everything in the scope of finish is completed. So you can nest asyncs and finish and so on. So that was, we felt, a more structured way to approach parallelism. And one of the motivations was you can get some guarantees. So, you know, yes, you can create threads in other languages, you can start them, you can wait on them, but if you have these low-level primitives, and this is a very trivial example, it's easy to create cases where you have deadlock, thread 1 waiting for thread 2 waiting for thread 1, and so on. So the intuition we had was that in extend, because of the nesting structure, you should be able to establish deadlock avoidance, because the only blocking operation was finish. So, you know, to have a deadlock, you need to have a cycle of finishes. But if you think of the execution proceeding as a tree, the weighting only goes upwards in the tree, so you cannot create a cycle. That was the intuition, and it was a correct intuition, but the properties still had to be proved. And so now in my class lecture, I talk about different ways of verifying programs. One is that you have a class of programs, like, so if you have parallel programs that are restricted to only using finish and async, then you can prove that any program in that class will never deadlock. Then we've got other kinds of verification where for a given program, or for a given program and given input, but this is like the universal one where a subset of features gives you some guarantee. So this deadlock avoidance is a great example. So this is the work that Jonathan and Jens did, where they created a featherweight language, which is Turing complete actually, and with the two parallel constructs, async and finish. So here's the grammar, and you can see they have iteration, but you can see async and finish showing up over here. And the semantic structure, which is very elegant, is a state is a program, and the array, which is a proxy for the global memory that could be accessed by all the tasks, and the tree. And the tree can represent a sequential composition over here, a parallel composition of subtrees, or a unit statement, or the completion of execution. And so in their paper, they had the small step operational semantics, where you could take a step in this triple, and you know the program is the same, but then the array could be changed to A prime, and the tree can be changed to T prime. And so just some of the rules, like over here, if you can step from T1 to T1 prime, and you have T1 followed by T2, then because of the sequential thing, you have to make progress in T1 first. So, or T1, you don't have a corresponding rule for T2, because you have to completely execute subtree T1 on the left of the sequencing operator before you go to the right. In the parallel case, however, you have an option. If T1 can step to T prime, and T1 is executing is logically in parallel with T2, then you can have the left subtree step to prime, or you can have the right subtree step from T2 to T2. So you can choose how to grow the subtree as it executes. You can take a step in the left subtree, the one on the right, because the two subtrees are logically can execute in parallel. And you have many possible executions, right, depending on how you make the choice. So that I thought was a very elegant way to capture the essence of parallelism. And of course, there were rules about the standard individual statements. And here was the program. We had the intuition, I mean the theorem. This is what we were waiting for, that Jonathan and Jens came up, is that for any program state, either you've completed execution, it's basically a progress theorem, or you can take a step. And that's essentially saying you cannot create deadlock with finish. So that was wonderful. And then in my, just to flesh this out, when I talk to the students, then I say, well, that's great when you have certain constructs like finish and async, and no matter what parallel program you write with finish and async, you're guaranteed absence of deadlock. But there may be some other properties that are not guaranteed, that are specific to a program. And this is where type systems come in, because then if the program is well typed, you can get some guarantees over there. And we've had the opportunity, inspired by some of Jens's work, to work on this. And these were colleagues at IBM, Satish Chandra, Vijay Saraswat, and a collaboration also with Ras Bodek, on type inference or locality analysis, because we had this rule that you can only kind of like dereference a pointer if the data is local, but you can pass global pointers around. So you have to make sure when you actually, I'm saying pointer, but it was really an object reference, that the actual dereference occurs when you're at the place where the data is located. So this type system did that. We've done some work that appeared more recently in eCoop on a linear type system for promises and permissions for race-free parallelism. So these were not directly influenced by Jens, but indirectly when I started learning about types based on Jens's work way back when I was at IBM. And then, of course, then what happens is that what if you don't have a type program and you want something, and then you can try to prove something for a given input. Even that is strong, because then for parallel program, you're proving it for all possible parallel executions of the same input. And for the same input, there can be many interleavings. And we've had the opportunity to do some work over there with futures and deadlock avoidance with futures and so on. OK, so that was one bit of a quick summary of some very major influence that the work done by Jens and his students have had on us. And so then I would basically summarize it to the students in my class, saying that you can have these 3 levels of verification for a whole class of programs, or a given program, so all input for a given program and input, but for all executions. And the lesson that we learned is the structured parallel primitives can really help these challenges, because you push more into this first class, which makes it so much easier to have guarantees. Oh, and just so you know, I also inflict on them. In every lecture I do, in the last 10 minutes, they do an in-class worksheet collaboratively. They're not graded, but they have to turn it in. So they can totally work 3 or 4 people, and someone can write a solution they heard from somewhere else. It's just like, did they grok the lecture or not? And so I gave them a featherweight extend or an extend program and said, OK, start evaluating it. We gave you a couple of steps. Like if you start with the program, here's the sequence, and do the step-by-step, and this is the solution. So they have to kind of go to figure out how one possible execution is not the only one with parallelism. And then I asked them, is there only one possible execution trace? And no, but they have to think about the fact that the parallel rule means you can choose one or the other. So hopefully they figure that out. And is there only one possible state? For this program, it turned out there were no data races, so it ended up being determinism. So even with this, I mean, this is to reinforce. I'm sure many of you have this experience too. The featherweight language like this can be a great pedagogic tool to help the students understand many of the fundamental concepts here. OK, very briefly now to wrap up. I'd mentioned the NSF Expeditions project. It was really great interdisciplinary projects where we had colleagues from computer architecture, software. Denny Aberle is a radiologist, MD, and so on. Compilers, good friend Sadayappan. So, and actually Jens was critical to connecting me with Jason Kong for participation in this project. I ended up playing an associate director role with Jason as the director. And there we had this model called concurrent collections, the one I mentioned earlier, led by Kath Nobe. And what we were able to do is use it as a way to schedule on a very heterogeneous platform. This is like 12 years ago, or more than, where we had a hardware prototype with CPU, GPU, FPGA, and you had this notation where you could create tasks that could be scheduled. And in fact, you had multiple versions of the same task. You could have a CPU version, a GPU version, FPGA, and there were scheduling advantages both in execution time performance and energy savings by choosing one or the other. But getting back to concurrent collections, the idea here was it tried to capture the essence of parallelism in a safe way, but as a coordination language without worrying too much about the sequential language within the task. And the coordination was in the form of a data dependence, whether like a producer-consumer, kind of like a key value tag. That's what a data item was. and what was called controller-controllee, where steps could be created asynchronously. So basically, you're capturing the essences of program dependence graph, data dependence, and control dependence. And we had different forms of notation, a textual one that could be processed by a compiler, what we do in PowerPoint, what we do on the whiteboard, but the same idea. And one, again, and this was really synergistic with Jens's work on featherweight extent, we needed a determinism property, a confluence property, because there's no shared memory, so there's no room. So we intuitively knew that all possible executions should lead to the same final state. But again, it took the collaboration of Jens to establish the main theorems over here. So we had this paper in the Scientific Programming Journal, and then here was the main theorem of determinism, which was, again, very, very helpful to us. And there are, thanks to that, we established determinism. We're no longer working on CNC execution, but I'm just saying, if anyone's interested, there's some other conjectures we have where the proofs are pending, like an idempotent one. You execute 2 copies of the same task, you should get the same answer. Parallelism one, meaning the semantics, if you execute things in parallel or sequentially, should be the same. That should be easier. It should follow from the determinism property, I think. Okay, so I think it's a good time for me to wrap up now. So what have I learned? Well, our community is much richer with you, Jens. And let's see. So I found Jens to be a real kindred spirit. We didn't really grow up in the same research community. I was more on the high-performance computing side. Jens, of course, in the PL Foundation side. But we could talk about any topic like parallel programming models, register allocation, more recently quantum computing. But as was alluded to at the start of the talk, and this was the 3 sides to Jens, so we've had really great discussions, especially when I moved from IBM to academia, about how academic administration works. And I remember even walking, when did we have that retreat on that ship, the Queen Mary? Remember, we just did rounds and rounds on the deck talking about some of this stuff. And more recently, Jens and I, along with many others, serve on the ACL, not many others, like a dozen others, serve on the ACM Council, and we've been having some discussions about some, very important topics related to the role of governance and volunteer leadership and so on, which has been incredibly valuable. And I think your intellectual curiosity is inspiring, and somehow I think it's always great to have Jens in the audience. So one reason I accepted this invitation was I knew he was going to be in the audience. I remember Jens was in the audience when I gave the Extend talk in 2005 because he had some question. The SSA workshop that in France that we had gone to, where I was talking about Ray SSA. So having Jens in the audience when you're giving a talk is really wonderful. And this is why I truly think of you as the ultimate PL Renaissance man. So thank you.